So it's going to be more of a talk about problems than solutions. Okay. And this work has a lot of this work has been done with people at INRIA, Microsoft Research, Aarhus, and various other places. So many, many collaborators. So the high-level takeaway is that crypto applications, and you have already heard this today, so this is maybe hitting you on the head too many times, are a high-value application for software verification, whether in lean or elsewhere. And that's because they are security critical, so people care about them. Often they have open specifications, and they're usually quite well-written specifications. The community is proof-friendly because cryptographers do write proofs, whether or not you accept them as machine checkable or not. And there's lots of interesting challenges. And that's what I'm hoping to convince you of and see if something sticks, right? And of course, when we think about crypto applications, here we are thinking things like Signal, of course. But then there's also very classic things like HTTPS, which all of us rely on. We think of as extremely boring and solved, but has some instructive lessons for us from how it was designed, how it went wrong, how people verified it. Okay, and I think we should heed those lessons. Because if you look at the lock button in HTTPS and you click on it, basically what's happening is it's a protocol called HTTPS, which internally uses a protocol called TLS, which is built using multiple cryptographic constructions, ECDHE, signatures, authenticated encryption, which themselves are instantiated using very specific crypto algorithms like NIST speakers, RSA, ASGCM, and so on. And of course, so what Sean was showing us was how to verify code at this level, but this protocol levels above. And Signal is kind of somewhere at that level of abstraction, let's say. So TLS is very, very old protocol, very classic. 1994, it was first introduced, didn't change so much since then. Until TLS 1.3, didn't change very much at all. And it had many proofs. Some of them were machine checked even, but had many pen and paper proofs and good proofs. Proofs were not wrong. So one might think that this is a completely solved problem, right? But before TLS 1.3 came up into 2018, this was definitely not solved. So this was, 24 years of bugs in the protocol, okay? And some of these bugs, the ones in green at least, were found at INRIA and Microsoft Research and so on. So and some of these bugs many of these bugs came up when people were trying to analyze the protocol. Formal analysis led to the discovery of the bugs. But I can honestly say that almost none of these bugs were found by a verification tool. Okay, so this was as part of a verification effort, but not discovered by verification tool. The other thing to realize is that these kinds of bugs, what is the shape of these bugs? Each attack, these are like well-known attacks with logos and web pages and news articles at the time they came up. The key part of it was it discovered or it uncovered a threat that had been ignored in prior proofs, okay? So when we talk about, let's formalize Signal, let's verify it, it's not a static artifact. The first model you make for Signal will be wrong in the sense that there will be an attack, which will come later on. We'll say, we forgot about this threat because it wasn't part of our threat model. You'll add it. You'll have to do a new proof. And this is how the field evolves. So cryptography is really an adversarial science where people attack, fix, And this is not a bad thing. This is how people even discover what the threat models are. It's not obvious when you start the project, okay? But let's also kind of expand out what went wrong in all of these things in TLS. Typically, it is in these categories. One is the crypto area, so where the crypto algorithm itself, which was thought to be strong for many years, turned out not to be so strong when the computers got much stronger. And nowadays, you're seeing a new variation of this, which is post-quantum crypto, where things that were strong before quantum computers will not be strong after quantum computers. And this is to be expected. Things degrade over time. But this also is the domain of crypto proofs. So pen and paper proofs, probabilistic proofs, relational proofs, about proving that the constructions that you're relying on do actually meet the guarantees you expect under the threat model that you are considering today, not the threat model that the designers considered when they designed it. The second category is protocol design flaws. Honestly, this is very rare. Okay? Even in Signal, even in TLS, what do we look at? If you find a design flaw, it's gold. I mean, you're going to find 1 in 10 years. It's not so common. And typically, the ones that you find are really kind of intricate interactions between different protocol modes. Each mode is actually perfectly fine on its own, but when you have the intersection of 3 or 4 modes or 3 or 4 subprotocols, often there are bad interactions and things go wrong. And that's a typical case. So this is sometimes called downgrade attacks or cross-protocol attacks. And the last one, which is actually the most common, as you can imagine, is implementation bugs. And they are all over the place, right? So there's memory errors, like Sean was showing some of these things in crypto code. But then in the protocol layer, there's often parsing bugs all over the place, right? So the machines crash when they parse stuff, but even if they don't crash, they might parse it incorrectly. If you incorrectly parse an X509 certificate or a JOT token, all your bets are off, right? And then there are state machines all over these protocols, because now we are no longer talking about, I'm just going to encrypt something and you're going to decrypt it. Well, I'm going to encrypt something, you're going to encrypt something back, then I'm going to encrypt something else to you. So there's actually a state machine going on. There's many steps. And if you get the state machines wrong, again, there could be bugs. And often what's interesting is on the attacks that I showed you on the previous page, it's almost like a multi-stage attack. So you often are exploiting some crypto weakness, some protocol design flaw, and some implementation bug to mount something which is truly exploitable. So the kinds of tools you need to analyze this are either you say, I want to have the super powerful tool which can analyze all of these, or you say, no, actually, these are 3 different categories of things. So I need 3 different tools to analyze 3 different kinds of things. And that depends on how you see the problem. So when you think about the design cycle of crypto applications, it typically goes through 3 phases, right? So first is high-level designs. It's typically a paper in Euro crypto, whatever, which says, here's a high-level design of the thing. There is a proof, usually pen and paper, but hopefully also machine checked, where you're really asking the question, is the math here correct? Is the security proof actually correct? Is it actually stated correctly? Is the theorem strong enough, and so on? And after that, it usually makes it into an open specification or a standard, right? And if that's for a successful protocol, lots of protocols never go beyond the first stage, but the ones that do, like Signal, like TLS, will become a published standard. And as for a standard, the questions are slightly different, because the standard is a medium of communication between different implementers, different users. So the question is it ambiguous? Is there 2 different ways of interpreting it? Is it still secure? Is it introducing new bugs because the parsing is not correctly defined, and so on? And finally, there are the implementations. And in the implementations, as you know, there's bugs, there's exploits, because often people don't care about bugs unless they're actually exploitable. And all of these things feedback. So this is not the case that there is never one version of a successful protocol. If you have one version of a protocol, you are not a success. So it's going to be a second version, right? So how do you feedback and go back and do this all over again without actually starting from scratch? So there's a field that studies this. It's sometimes called high assurance cryptographic software. It's sometimes called computer-aided cryptography, computer security foundations. And there are conferences devoted to this. And many people at INRIA work on this area, which is about applying machine checkable proofs to the design, analysis, and implementation of crypto. And there's a nice paper that I and many others wrote that you can read to get a survey of the area. It's 5 years out of date, but it's okay. It'll give you a sense of where we were at least 5 years ago. And the whole point is there's multiple levels of things you want to do. You want to analyze the design, you want to analyze the standard and specification, and you want to analyze the implementation for finding different kinds of things. And you want to do this over and over again as the system evolves. It's not for a snapshot, right? So proving a snapshot, many of us have done, and it's doable. You publish the paper, you move on. It's not something usable in real life, because the software has already evolved. The design has already evolved by the time you publish the paper. So a lot of the work I'm talking about here was done both here at this team called INRIA Prosecco, and some of the work since 2021 is done as part of my company, which is called Crispin. So let's look at the first thing, which we have already looked at a couple of times. So I'll go pretty fast, because when we talk about crypto, the first thing we think about is crypto library. So we have to address this. So when you think about crypto libraries, all of us are using a variety of crypto libraries every single day. Okay, it's not just one. If you have a Windows machine, you're probably using the Windows crypto library. If you have a Mac, it has its own. Android has its own. OpenSSL is running on most servers. Firefox has its own crypto library. Your ARM machines have their own crypto library. There's tons and tons of crypto libraries for different use cases. Okay, and of course, most of these are not verified, the ones that we are using today. But in fact, there's a whole bunch of verified crypto libraries. It's like a very vibrant field. There are things that have been verified in ROC, things have been verified in EasyCrypt, in FStar, as Sean showed, also in Lean. Amazon uses Hall Lite. Other people use Isabelle Hall. Every single proof assistant you can imagine, and some which are more domain specific, have been used to verify a wide range of crypto libraries. Okay. And so the good news is that if you think of any modern crypto algorithm, any of them, there is most likely an open source, formally verified implementation of that algorithm you can use today. Okay. And so there is no excuse for you not to use non-verified algorithms. So it's a big success story, I would say, for formal verification in this domain, that it has actually caught the imagination and been practically employed by Amazon, by Google, by Microsoft, by so many other people everywhere. And these are mostly mechanized proofs that you can run yourself, and the proofs are also made available in open source. And what does these proofs look like? We looked at already. I don't want to go into the details, but at a high level, you take the standard, you extract out a formal spec. Sometimes the spec is executable, which is nice. Sometimes it's not, just still okay. You have an implementation, which is either in C or in Rust or in assembly, and you verify that the implementation meets the spec. And that's called functional correctness. If your implementation was in assembly or in C, you also care about the fact that it shouldn't crash your memory, because it should overwrite memory it's not supposed to write to, so you also need memory safety. For Rust, you have certain kinds of safety guarantees built in, and other languages also. And the third category that you're really worried about, and in fact, if you ask a crypto person, the category they are most worried about is not correctness, not memory safety. I mean, of course, those are taken as guaranteed. What you worry about is side channels. Because if you have a side channel attack, you might be losing secrets. It's not just your machine crashes, you're losing secrets that are very valuable. So you want to verify for these kinds of properties and keep fixing, re-verifying, fixing, re-verifying. And this kind of stuff we have done, other people have done. So for example, the Hacklestar, Whale, and Evercrypt libraries that were developed as part of INRIA and Microsoft Research's collaboration with Carnegie Mellon University as well, basically verified a whole bunch of algorithms written in C. Actually, they were written in low star and compiled to C. All the proofs are done in F star. This is 250,000 lines of code, which produce about 135,000 lines of C and assembly. This includes, of course, Curve 25519, ED25519, everything you can imagine. Okay. And just to give a sense of the effort required in those days, this is a few years ago, there's 3 or more PhDs spent their entire PhDs working on verifying this code. Okay. And since the code was written, for the last many, many years, people like Jonathan and Imeric, who are in the room, have been maintaining these proofs. And it's not a zero-cost effort. It's very painful to keep maintaining the proofs as the tools evolve, as the compilers evolve, as people keep asking you for more and more kind of platforms that you need to support. So this is a living artifact, and it's been a success story, but also a lot of work. And this is something we hope we will never have to repeat again, and nobody else will have to repeat again, because now we can do a lot of these interesting proofs using automation and tools like Lean, but also using AI. But just to give you a sense of also what other concerns you might have when you do these kinds of proofs, this is a typical spec that we used to write in F star for field multiplication. So it's modular multiplication. So there is a function which has an output buffer and 2 input buffers and a temporary scratch buffer. You have to have memory safety annotation saying what pointers are live, which are disjoint from each other. And then your post condition also talks about the disjointness of buffers, what actually, not disjointness of buffers, what was actually modified by this function, and then finally a functional correctness spec saying what the function actually does. So the advantage of living in the Rust Lean world is, or Rust world, to be honest, is that you can just focus on the last bit, right? What was the function doing? Not all the memory stuff. The memory stuff was there because you're compiling to C and you were following the C memory model. But at the same time, you have to ask the question, well, who is expected to write and read the spec, right? So in this world, it was the proof engineers. It was us who wrote the spec, not the people who were going to actually use the C code. They didn't want to see the spec, right? And not the people who actually wrote code as their main career. So the lessons from that project is that, first thing, performance must be very high. And this is, I think Sean hit this as well. Performance must match that of unverified code, otherwise people are not going to use your stuff, right? So you can change the code, but it has to be at least as fast. The code must be reviewable, okay? So the code we were deploying was things that people actually wanted to review before they put it into Firefox or Linux or Python. They actually want to review this code. Now, this may be less important in the world of LLM-generated PRs, but I think for a lot of these open source projects, you will still find that the code that you produce must be reviewable. And the third thing is that you don't know how many platforms these things run on. They run on a lot, including Spark on some weird configuration and so on. And so for crypto libraries, often you have to deal with a lot of constraints which you normally don't think of when you're writing your beautiful Rust code in your on a 64-bit Mac OS machine. And then building and maintaining these proofs took a lot of effort, because for C code, memory safety dominated the annotation effort, like I showed you in the previous slide. With Rust, that becomes less painful. Automation was key, and in our case, it was automation using SMT. But any kind of automation is key because these proofs are huge. And because we were using SMT maybe, but I think also because we were relying a lot on nonlinear arithmetic, because that's what this code is like, a lot of proofs ended up being fragile. So proof maintenance was actually a big pain point for this project, continues to be a big pain point. So for whenever we say we're going to embark on a big challenge like signal shot, I always think about, okay, the first version, no problem. I can imagine it being done. How are we going to maintain these proofs? That's going to be like key, and whether that's actually doable. Can AI help us do this? I don't know, but that's actually a key point for this kind of effort. And the last lesson, which is something I take from it, but it's not clear that everybody will agree on this, is that the proof effort and the specification effort, at least, must involve developers, because often the developers are the ones who know what they're thinking. And for us to have to discover that is almost half the work of what they were thinking when they write the code. So when we decided we wanted to verify post-quantum crypto, we did something completely different, right? So we did something closer to what Sean is doing, which is to write code in Rust and verify it using F-star, the same language that we used to verify Hackle-star. Now the toolchain we are using is also supporting Lean, and we are also kind of merging efforts with NAS and using NAS to generate the Lean. So you won't see too much difference from using NAS when you use this for these proofs in the future. But with one difference, okay? So let me give you an example. So the code that we write is in Rust, right? So this is a reduction function. It's called Barrett reduction. It's used in MLChem. So Barrett reduction, basically, what you really want to do is you have a signed integer called value. You want to do the modulus of this with respect to the prime 3329. And that's what you want to do. But modulus is not a constant time operation on most platforms. And so instead of doing a direct modulus, what you do is you do this kind of shift and addition and multiplication, which are believed to be constant time on most platforms. So you use this formulation of modular reduction. Okay. Now, we didn't even invent this. This is what was in the MLChem reference implementation. So we just take that. Okay, it's a classic algorithm. But of course, there are these pluses, minuses, stars in there, which can overflow. Okay, this is signed integers. Okay, signed integer arithmetic in C, if it overflows, is undefined behavior. In Rust, if you use this and you in debug mode, it'll panic if you overflow or underflow. In release mode, it won't panic, but it'll silently just wrap around the arithmetic. So it'll give you answers that you didn't expect, okay, which might be actually worse than panicking in certain cases. So even though Rust is memory safe, you still have to worry about, well, what if I access an array or a vector beyond its limits? Or what if I do arithmetic which overflows or underflows? Because this will cause a crash at runtime, right? It's a panic. So to both avoid panics and to give you functional correctness, what we do is we write our specs in Rust, okay? Because this code was actually written by one half of our company is all crypto engineers who don't do verification. One half of our company is people who do verification and who don't know anything about crypto. So this was written by people who are crypto engineers. And so they needed to be able to write the specs in Rust so that they understood it, right? So this was the spec that they came up with. This is like the value has to be between a certain range and a certain range, and the output is going to have this mathematical property. It's not very surprising, but it's written in Rust, right? So they can read it. They can actually write asserts with these values, and they can actually check that this is passing tests at runtime, that this precondition always holds when you call the function. This postcondition always holds when you exit the function. And if you give that pre and post condition, and you take that function that I showed you on the previous slide, you compile it via hacks to F-star and give it over to F-star. F-star verifies it completely automatically using SMT, because it's bit vector arithmetic. It's easy, okay? Even in Lean, if you give that function to Lean and ask it to verify it, it's going to, if you give it BV decide, almost all the work is done. You might have to add a couple of instructions, but really BV decide will solve that problem. Okay, so it's an easy to verify thing. So it's a very bad example in some sense. For some of these kinds of functions, you have a proof, but it's not very deep. It's kind of along the lines of the proofs that Sean was showing you. But the key point I want to show you here is that the specification here, like we were discussing towards the end of Sean's talk, is written in Rust, is meant to be written by developers, and it's definitely meant to be read by developers. so that tomorrow, if they add a new call to this function where they violate that precondition, they can go and see, I violated that precondition. It's not something hidden deep inside the proof. The other thing is, well, what do we do about side channels? We are in Rust, so we can do very little about side channels. We can try to remove, kind of write in a constant time style, and that's what we call secret independence, which is a set of rules that you put in your source code, enforced by the Rust type system. So it's all like for free in some sense. But the compiler may reintroduce side channels. We have no guarantee that it won't do that. Okay. Plus, of course, below the compiler, there could still be microarchitectural attacks and so on. But at least you can check that your source code is constant time or secret independent. And you can do this just by using the Rust type system. So that's kind of a nice feature. And this, a lot of people like when they use this. And just to give you a sense of it, while we were doing secret independence for our code, we found a line of code. This is in C code, but actually we found it in our Rust code, where there was a division here with respect. On the left-hand side of the division was some value which is supposed to be secret. On the right-hand side of a value was something which is supposed to be public. But since you were doing division with a secret value, we couldn't prove secret independence. The type checker failed. So this was a genuine case where the type checkers told us, hey, I can't type check this. And then we realized this could be a bug. So we rewrote it differently. And then we looked at all other implementations of this out there, including the reference implementation that the Kyber authors had written. And we found the same thing over there. And this eventually led, with a lot of work by a lot of other people other than us, to a paper called Kyber Slash, where they showed that this bug is actually exploitable. And this won our best paper award at Chess last year. Again, we did nothing. We just noticed a division. Everything else was done by the other clever people who knew how to exploit this, right? A lot of work needs to go between a bug like this and an exploit. So what lessons shall we take from this part of the thing? Well, it's the first limitation I would point out is that from Rust, side channels are very hard to prevent because there's a lot of low-level things that we can't see because it's not in our runtime model, okay? And the compiler might do bad stuff. So one might say, well, you should not write stuff in Rust, and this is what a mini cryptographer says. You should just write and verify everything in assembly. But of course, I'm hoping that this room does not share that sentiment because, well, maybe AI can write assembly and verify it. I cannot, right? The other thing that we have found with many of our developers, but also developers at other companies, is that the verification flow has to fit whatever the crypto developers need. So at Microsoft, this might mean that they have to write in their style, and then you have to do your proofs. For many of our customers, it basically means that they can read and write Rust or C, but they are unwilling to look at F star or Rock, probably Lean as well. They're unwilling to look at that. Okay. At the same time, even though we are writing code in beautiful Rust, often some projects are not capable of accepting Rust code. So we still have this ugly compiler, or the compiler is beautiful, Jonathan's compiler, but it produces C code. And just so that we can provide C code for projects to integrate into their C projects, although we would love for them to take Rust. Signal uses our Rust code, so that's good. Okay, and supporting multiple platforms is a pain for any small project. So you have to really test your stuff very well on multiple platforms in order to find bugs. But here, there's challenges and opportunities for Lean. Okay, and the first one is, of course, side channels, like I said. So the tool Jasmine has a set of very nice custom analysis for preventing various classes of side channels, including the ones I showed you, like side channel, like secret independence, but at the assembly level, and also certain classes of speculative execution attacks. These are all custom handwritten tools. Could we port them to Lean? Question. To do that, you actually need a model of the runtime, which is precise, which actually exposes these attacks. Could we formalize such a machine model in Lean? We would need that to do that if you want to get any kind of confident analysis against side channels. The second thing is we're still trusting the Rust compiler. Sean is, I am. And so how do we remove this trust? Do we rewrite all our code in assembly and verify it there? I'd rather not, but people have done this. This is what Amazon does. This is what Jasmine and Whale do. Or could we verify a subset or the full Rust compiler in some way that we believe? Big project, but this is what we would have to do to remove that trust barrier. And finally, a lot of the proofs that we're doing, we really need it to be automated heavily. And so obviously AI plus grind, like we saw today, might be the answer. But this is certainly a challenge right now. Hopefully will be less of a challenge going forward. Let's lift up to the protocol level, right? Remember, like we had all these issues in TLS and so on. There was one project that we all worked on, including Cedric, who's here, and Microsoft Research people, and INRIA people, and so on, or called MeTLS, where we verified an implementation of the TLS protocol. It was TLS 1.2 at the time, and then it got generalized to TLS 1.3. And this is a very large project, 30,000 lines of code, 100 plus modules. And during this verification, major attacks on TLS were found. So in that sense, it was very successful. It also influenced the design of TLS 1.3. But during this, we also learned many lessons, which is that when you have large protocol specs, you have to treat them as complex distributed systems. And they're not just about the crypto, they're not just about the protocol. They have lots of details you wouldn't imagine. They have, of course, state machines, there's message formats, there's multiple kind of modes of the protocol that interfere with each other, causing downgrade attacks. And the only way we could get trust in our specification, even to know because it's so large the spec, was to write a reference implementation and verify it. So, I mean, it wasn't just that we were trying to verify an implementation. In fact, that was the only way of verifying the protocol itself, to actually write a reference implementation. Otherwise, you would never be sure that you got all the details right. However, we were trying to do proofs kind of somewhat monolithically in one framework, and that was very hard to scale because there are many little bits of the proof that really require specialized treatment. We tried to do as much of it as possible within F-star, within one framework, but there were limits to this. But we went quite far, I would say. So we proved cryptographic security in F-star using a variation called computational F-star, which led in the future to a technique called state separating proofs, which underlies many interesting tools. We proved parsing correctness using a tool called everparse, which then led in a future iteration to something called comparse. We proved memory safety using a language called Lodestar. So a lot of techniques came out of this, which then kind of farmed out and became other kinds of analyses. But today, if I wanted to verify TLS, I would never do it the same way, because that was about generating C code. It was written in F-star. We had to write the implementation ourselves because no self-respecting TLS developer would write F-star, right? So we had to write it. But now we write stuff in Rust because, again, half of our team knows Rust, knows crypto. They don't know formal verification. So BERT is an implementation, it's proof of concept implementation of TLS. It does post-quantum TLS. It's really a research artifact. You shouldn't kind of treat it as a serious implementation, but it is fully featured for TLS 1.3. And it's verified using hacks and multiple different backend provers. So we use F-star, we use SSProve, and we use ProVerif for different kinds of properties, okay? So for the protocol logic of TLS, and on the right-hand side is the high-level protocol, and this is what you would think of as PQXDH or SPQR or whatever. This is where we use ProVerif to analyze it. So we take hacks, we take the Rust code, we compile it to ProVerif, and then we run ProVerif to analyze the output for authentication, confidentiality, the classic protocol analysis that you would want to do. We also do post-quantum analysis here by assuming some post-quantum secure CAN. So from 1,700 lines of Rust, you produce about 6,000 lines of ProVerif, which you can analyze. So the ProVerif analysis, this protocol analysis, is happening on the code, but using a very domain-specific prover that has been developed just for protocol analysis. Then there is the key schedule of TLS, which is a bunch of key derivations that it does. And this you can think of as I don't know what part of Signal this is. But Signal also has this kind of key schedule. It's implemented in Rust. But here, what we did was actually we redid the pen and paper proof done using state separating proofs of this key schedule in prior work by some of the people in this room. And basically, Bas Pitters and his students use hacks to translate this to SSProve, which at the time was written in Rock. Now there's a version of this also in Lean, and mechanize this pen and paper proof, okay? Which is a computational cryptographic proof, which has its meaning in terms of probabilistic polynomial Turing machines. So it's a very different kind of proof than what ProVerif would do. And the third kind of thing we did, we took the Rust implementation, well, the protocol core of it, we translated it into F-star and proved runtime safety, which means that we wanted to prove that it would never panic on no matter what input was given, well, of the code that we verified. And then we also proved that the parsing was correct. So that whenever you parse a message, and if you parse a message that was serialized correctly, you would get the right result. So these are three different kinds of properties using three different tools, okay? It's unclear whether any one of these tools would have been able to, well, I know that one of some of these tools would not have been able to do the other properties, but it's not clear whether there's any one tool that could have done all of them as efficiently as we. Okay. So the lessons from that project is that the choice of programming language and the spec language is key for adoption, because in fact, the programmers are willing to do certain kinds of things, crypto developers, other things they're not willing to look at and review and so on. And we used multiple task-specific provers to reduce the verification effort, okay? Completely different strengths for prover if S is proven F star, but this also means that there is no connection between them. So there is no end-to-end security theorem. And so they're all in completely different frameworks, right? There's no formal link between them. Some things have some kinds of guarantees, some other things have different kinds of guarantees. And this similar theme comes to when we look at Signal. So what's the time?
So you still have 25 minutes.
Good. So 25 is enough. All right, Signal. So this is where the Signal shot comes in, right? So we've already been working with the Signal team to verify some of their post-quantum protocols. And you've heard some of them mentioned earlier today, called PQXDH and SPQR. And let me talk to you a little bit more about this and what we have done and what this indicates maybe for Signal shot. So the classic Signal protocol that if you all, how many of you have Signal installed on your phones? Yeah, okay, good, well done. So when you first initiate a conversation with somebody you've never met before, it uses this protocol called X3DH, right? What it does is downloads their keys from the Signal server, and it basically does these 4 Diffie-Hellman operations with respect to the different keys it's downloaded and your own keys, and it creates a new session key, and it encrypts the first message to the person you're contacting. And when they respond, you start a new protocol. It's called the double ratchet. So with every response that's coming back and forth, you're refreshing the keys using a new Diffie-Hellman. So it's tons and tons of Diffie-Hellmans. So 4 Diffie-Hellmans first, 1 Diffie-Hellman per message as you go through the protocol. And the key guarantees here is that you get mutual authentication. Both parties know who you're talking to. There is a caveat, of course, because you're downloading the keys from the server. So you have to, at some point, check the QR code of somebody you're talking to be completely sure that you're talking to the right person. But as long as you at some point check the QR code of your peers, you get mutual authentication. You also get this forward secrecy, which means that at any point, if somebody compromises your phone, they can't read prior messages. You also get a much stronger property also called post-compromise security. You're passing through security in some shady airport. They take your phone away from you and they hand it back to you 10 minutes later. You're worried, oh, maybe they have gotten all my Signal keys right now. If you quickly send a message to everybody and everybody responds back, the keys are now safe. So it's kind of, even after your keys have been compromised, you can do certain actions to heal this compromise, is basically the idea. And then they also provide a certain form of deniability. Different people contest how valuable it is. I don't see it very valuable, but it is something that people do care about. So it does provide that too. So this is all the properties that this protocol is these protocols are intended to give you. So at some point, they said they wanted a post-quantum version of this. So they decided, they designed this protocol called PQXDH, and they published a first specification for it, started rolling it out to selected clients. And the basic idea there was, in addition to these 4 Diffie-Hellmans, you do 1 post-quantum chem, and you mix in this 1 post-quantum chem-protected secret, which is SS, into the same. We're already having 4 Diffie-Hellman secrets, just throw in 1 more secret, which is the post-quantum secret. And that's a minimal addition to PQXDH. So you can see even the protocol, you're only adding certain steps in certain places. It's purely an additive change. And the whole point was Signal has such a high reputation that they don't want to mess with what works, okay? They didn't want to remove some Diffie-Hellman just because they have the chem. They're like, no, we keep everything that people love about us, and we add this additional bit of security. So it's a very small addition, and the previous protocol had been widely analyzed. Pen and paper proofs, machine check proofs, formal verification, everything had been done for classic Signal. So the question is, well, A, is the new protocol at least as secure as the old protocol? It should be a no-brainer because you're only adding things, okay? And the second one is the new protocol secure against a harvest now, decrypt later quantum adversary, right? So adversary who cannot tamper with the session as it's happening, but maybe later on records the message and later on tries to break the session key. So what we did, and this is a joint work with several people, is we formalized these PQXDH protocol. To formalize such a protocol, you first have to say what your protocol model is, what the protocol is supposed to do, of course. You have to formalize all the crypto assumptions you're going to use. For example, is Diffie-Hellman secure, not secure? What your security goals are, which may not be obvious, but let's say you have to kind of figure that out. And a compromise model, which means what keys, what secrets can be known to the adversary and when, okay? And often this is actually the trickiest bit for protocols like Signal. And then what we did was we took that protocol specification, we fed it to the tool, Proverif, again, what we saw in Bertie before, and analyze it. And the way we do it is you analyze it, it shows you an attack, and you say, oh, it's an attack because I screwed up something in my protocol model. So you fix the protocol model. Again, you go around and round. But sometimes the attacks it shows might actually be a bug in the protocol, right? Once you have fixed the protocol spec to not have any attacks, the idea was, well, now you can do a proof. Okay, so Proverif is great for finding attacks. It does give you a symbolic security theorem, but cryptographers don't like the symbolic security theorems, they don't believe it. So they want to see a proper cryptographic proof, like pen and paper style and so on. So there's this other tool which uses a very similar input syntax to Proverif called cryptoverif, also authored by Bruno Blanchet, who's here. I mean, who's not here, but who's in the building. And you can basically feed almost the same input. It's not exactly the same because the crypto assumptions have to be written differently, the security goals are differently, and so on. And you can feed it to cryptoverif, and cryptoverif will try to do a game-based proof of this protocol. If it can't do it, it'll ask you for help, and you can give it hints. It'll do a game-based proof, and finally it'll say, yes, it is secure for all the properties that you asked for. So this was our idea. We'll use Proverif to find bugs, and we'll use cryptoverif to do the security proof. This is what a Proverif model looks like. Okay. The reason I'm going to show it to you is because it's different from a lot of the crypto things you've seen so far, which are more functional, like mathematical. This is a protocol. It's giving, sending, receiving. So the initiator is downloading the keys, doing a bunch of crypto checks, and going to send a message. And then it might receive a message after that. Then it does another bunch of crypto checks. So you can think of this as a interleaving between messaging, input, output, some checking of cryptographic stuff, some construction of new crypto stuff, maybe putting something into a database, which in this case is modeled as a table, doing some security events saying I'm done or I've been compromised and so on. So these are all the things that you need to model about the protocol. And this is actually one of the simpler models. There's only two parties and there's only one message. Okay, typically the models can be quite complicated. And this syntax is basically called the applied pi calculus, which is the input language of Proverif. And the main idea there is to make everything super precise. When, what can happen, what is the computation that is being done. And if you feed that in and you give it a query, and the query is basically a security query saying, I would like to prove, and this is what this query says, I would like to prove that whenever Blake says that it's done and it has finished a session with A and B and SPQR and these parameters at time I, it must be the case that the attacker does not know the secret key. And it must be the case, or it must be the case that something has been compromised before. So you can write these kind of secrecy queries. You can also ask authentication queries and so on. And Proverif will analyze all possible traces of the system. And note, these are not finite traces because they are operating, the protocol is operating in combination with an unbounded adversary, unspecified adversary, who can send any number of messages of any size to Alex and to Blake to try to confuse them. And you want to say in all possible traces with all possible adversaries, can you ever find a trace in which this particular property, which is my secrecy property, is violated? And Proverif will either say, no, I couldn't find something, in which case you have a symbolic security theorem, or it'll give you a counterexample as a trace, and it gives you a trace, something like that. Okay, and you can try to read the trace and understand it. Honestly, Claude is very good at understanding those traces and making you a nice picture. So you might want to kind of just use AI to understand what the trace means. But it's a very precise trace that tells you exactly what the attack is. And cryptoverif, it's pretty much the same protocol model, but then you have to give it a proof. And the proof in cryptoverif looks something like the thing on the right, where you say you start with the original game, then you're going to apply this UFCMA corrupt game, then you're going to get an output game, which I'm going to save in g1.cv so I can look at it later. Then I'm going to do some syntactic transformations, and I'm going to apply another game, then go to some more syntactic simplifications, apply another game, and so on. And these game transformations are going to finally yield a game at the bottom, which is trivially secure. And each transformation has been vetted and proven elsewhere as something that is preserving the security of the protocol. It's not adding security. It's reducing security, but with a small negligible amount. So with this game-based proof, you can basically get the security of the protocol. Okay. Of course, then we also talk about quantum adversaries. And quantum adversaries are somewhat new in the field of formal modeling, and we have to be careful about it because even with Signal, because it's claiming to be post-quantum secure, now we need a model of what a quantum adversary can do and cannot do. And in Proverif, in a symbolic model, it's very easy. You just say, oh, quantum adversary breaks all Diffie-Hellman or something like that. It's very crude, but it's easy. In the computational model, it's much more subtle. And in fact, there's a nice paper on how to do verification against passive quantum adversaries in Cryptoverif, and other tools like Squirrel and so on have put a lot of work into modeling quantum adversaries. This is something which is not a trivial task. If you do these proofs in Lean, this is an aspect that will have to be replicated as well. So what came out of this? Well, the first slide I showed you, I said a minimal change, right? So the minimal change was we were going to add this new key, the post-quantum public key, to the protocol. And so in Signal, what happened is the post-quantum public key is signed because you don't want anybody to put the post-quantum public key there. So you sign it with the identity key, with your own identity key. So if your device uploads your post-quantum public key, it's going to sign it with your identity key. But there's another key up there, which is also signed with your identity public key, which is the Diffie-Hellman public key. So what the attacker can do is actually swap the two because they both sign with the same key. And so if you swap the two, what is going to happen is that the person that you're speaking with, when I download your key, you've swapped, and the attacker has just swapped your two keys. I'm going to try to do post-quantum encryption with your Diffie-Hellman key, and I'm going to try to do Diffie-Hellman with your post-quantum key. And when you do this kind of thing, all bets are off, right? In practice, this cannot really happen because the post-quantum key is 1 kilobyte and Diffie-Hellman key is 32 bytes. So somewhere before you actually did the crypto, some code will fail out and it'll say, no, the sizes are not what I expected. But it's not something which is it's a specification bug, not necessarily exploitable, and it's not exploitable in the Signal implementation, but this is something that you have to be careful of. And this is a classic case where you have to worry, and this is an attack that Proverif could find, right? Because the key encodings, the encodings of these two were colliding. Okay, this is also something that a tool like Compars, which Theophile designed, could have found this as well. Now you look at this and you say, well, I just added one thing. But the interesting thing is adding the new thing broke the old protocol. This is not only breaking PQXDH, but this new key that you now publish under your identity key could be used to break X3DH, because now you have a new signed key that you are publishing that somebody could use to attack your sessions with the old protocol. Okay, because now this could be used in the old protocol. So seemingly innocuous additions can actually have very bad interactions across protocols. Okay, so this is something that Proverif could find, and it's representative of a general class of cross-protocol attacks. People have been finding this in TLS and other things for years, so it's not surprising to someone who knows protocols. But this was surprising to the Signal people, and of course it is easy to fake. So you just add enough domain information that these two things don't clash. Okay, and the Signal implementation already checks for lengths and makes sure that they don't collide and so on. And long-term fix would be to use actually a more reasonable kind of framework for doing all your cryptographic formats. And of course, I'm going to advertise Compars because it's by Theophile, my student. So the success story there was they published the spec. We did the formal analysis. We found these issues. We told them the issues. They published a new spec. We did a proof. And we proved that the new version, V2 version or whatever, was secure. And this whole thing from beginning to end took 1 month, 1 calendar month. Okay, and so this was the kind of what you can do with humans, right? Doing proofs, and you can imagine the speed ups you can get if you set your formal verification up correctly, how far you can get. But the next project that we were engaged with Signal is SPQR. This is also something that you saw earlier today. So SPQR is their version of the post-quantum ratcheting protocol. And here we use a different style. So here the Signal designers, after the PQXDH experiment, they didn't want it to be the case that they did the first design, they gave it to us, then or they didn't give it to us, they just published it. We went off and did our proof, and then we gave them the result. Then they did a new thing, then they maybe went off and did our proofs and gave them the result. So which has been the classic mode of researchers and protocol developers. Protocol developers do their thing, then the researchers go do their thing, and then they go back and forth. This time, they didn't want to have that middleman, basically. They said, we want to analyze stuff ourselves because we are experimenting with they had about a dozen variants of SPQR that they wanted to analyze. They didn't know which one they were going to pick. They wanted to choose them primarily based on performance, but also they wanted to make sure that whatever they pick was secure according to the definition of security. So they took, in collaboration with us, they built a pro-verif model of SPQR from the very beginning. And from the very beginning, all their designs were basically accompanied by a pro-verif model. So they were analyzing it for performance using some proof of concept implementation, but they were also always analyzing it for security using pro-verif from the very beginning. And pro-verif was the syntax that they found most comfortable to use in this case. We also offered them, listen, you can write it in Rust in this way, or you can write it in some other stuff, but they were happy to use this tool because it was giving them very quick feedback on small changes, and it was able to find attacks. And I can't emphasize this enough. When we are using proof assistant, when I'm using F-star, when we're using Lean, we are focusing on producing proofs, which is the right thing. Of course, we want to produce proofs. But at the design phase, what is most valuable for a lot of these crypto developers is attacks. They want to make mistakes and see that, okay, it catches my mistakes. Because then when they don't make the mistake, they have confidence that it was actually correct, right? If you don't see any attacks in your protocol ever, you don't know whether you're verifying anything meaningful at all. You want it to fail, and then you want it to succeed. That's the psychological profile that makes you feel confident, okay? And even when it succeeds, you feel suspicious. So you add in a failure just to see that it'll catch the failure, because you cannot be sure at all. So pro-verif was very useful for them because it was fully automated. The syntax was pretty clear, very stable for many years, and it was able to find attacks. Okay, so they did this many, many times. They did for all 12 variations. They had a little help from us because pro-verif in the beginning was not familiar to them. Now they are completely familiar with pro-verif. They use pro-verif. So once they've settled on a design, actually they settled on 3 designs. They actually implemented all 3 designs in Rust. And at that point, they were like, okay, from the very first moment when we are using Rust, let's try to plug in the verification framework so that we don't come back like 6 months later and say, oh, if only we had done it in a different way, it'd be easier to verify. So from the very beginning, they were using hacks, which means they were using preconditions, postconditions in their code, trying to write everywhere what they expected to be the conditions for panic freedom, what they expected to be their assertions, and so on. And they annotated their code from the very beginning. And this was, to begin with, a little bit painful because our tool was bad, not working very well. And in the course of this, they kind of influenced us to improve our tooling a lot, and they got very good at writing the specs that they cared about. Okay, and this is another thing that I would emphasize, which is that we can't sit out here not being the Signal developers and tell them what they should verify or what they should care about. They have their own things that they care about, and we might be able to add to them, but we can't just sort of take over and imagine that we know everything that they have in their heads. So in the end, this is what the artifact is. It's actually on their main repo. It's running under CI. The security proofs run under CI. The correctness proofs run under CI. The correctness, I would say, functional correctness is for very, very small part of the code base. There's a lot more work to be done. I would say almost functional correctness, you can almost ignore it. It's so small. It's the runtime safety, which is for a good chunk of the code base. There's a protocol security, which is for just the protocol layer, the unchunked protocol layer, and so on. So there's a lot more work to be done to make that code base kind of trustworthy, let's say. And I think a lot of this can be done as part of the Signal Shot challenge and will be. But I'm just kind of giving you the information on what we learned while we were doing this. So Bertie and Signal, 2 protocol experiments that we did, implementations that have security proofs. What did we learn from them? And what are the challenges and opportunities they put up? The first thing is that the developers wanted to be able to incrementally design the protocol, discover what threats that they needed, and then find automated attacks. This is like very important for the Signal people. But if you look from a very far away, even in TLS, this is very important because the protocol evolves version by version. The threats that you think about when you first design the protocol are not the threats that you think about for version 5. And unless you can find attacks, people don't really trust you or believe that you're doing the right thing. So being able to quickly experiment is going to be key. And so whatever we build, even in Lean, if we need to have some kind of attack discovery mechanism that we can plug into it. Of course, for the final protocol, just having an end-to-end perfect proof is key, is important, and I think that's for sure on the roadmap, but I want to put the attack discovery on the roadmap as well. The second thing is that all the stuff I showed you was like, okay, I'm using this tool for this, that tool for this. None of these things connect, right? And so obviously you would want to have like an end-to-end framework that can prove all of these things in a single framework and all the proofs connect. And this has been done before. It's not like you have to invent this from scratch. If you look at the Formosa crypto project, this is an amazing project where they use EasyCrypt as a proof framework for doing security proofs, for proving assembly proofs, and also side channel proofs. All of that in the same framework in EasyCrypt, okay, which is a domain-specific framework, fairly general purpose, but still domain-specific for doing all these kinds of proofs in one place. Rock has been used for doing a whole bunch of these kinds of things as well. F-star was used for doing a whole bunch of these things as well. And I think what we are proposing now, that Lean should be used for doing a whole bunch of these things, but maybe we can learn from these earlier projects, both their successes and their failures. In particular, there's a lot of domain-specific knowledge, and Bass has been working on some of this, I know, in EasyCrypt and Squirrel, in all of these tools. And it's not like these tools were just invented because people wanted their own tool. They all have their strengths, and they all are able to do certain proofs very well. To be able to import those proof techniques into a single framework like Lean will require some interesting work, make sure that we are able to use the best ideas that came from all of these, a large body of work that exists already. And the final thing, and this is more personal to me, I think from the users that we talk to, including the users in CycRispR and the users we talk to in Signal and other places, being able to reflect the assumptions and the theorems in the source code is important to them. So this may not be the exact same use case as SymCrypt, but for some of these other people, they really want to read and write the security annotations there. They want to see what they are breaking when they're breaking it and be able to modify it. So writing annotations, they're not super enthusiastic about, but being able to read what the precondition or the postcondition is, they really want to be able to do that. So we need more tooling to be able to do this. But of course, nobody wants to see the proofs, okay? So they don't want to see the proofs. Even I don't want to see the proofs. So we don't want to know the proofs exist, but we don't want to see it. But the theorems, we want them to be like really understandable and reviewable by the users. So I'm going to conclude there. My main message here is that formal verification has already had a big impact on real-world crypto and can continue to do so with projects like Signal Shot. Just to summarize, if you're using any modern crypto web browser, most likely the crypto library is already formally verified or parts of it, and otherwise they're almost going to be. There are verified designs and implementations for a lot of the protocols that we care about today. But there are some new interesting challenges that come, I hope you've seen, from doing security proofs and doing software proofs. And this is not exactly math. Okay, so I'm going to resist that argument that because Lean can do math, it can do all of this stuff. I think there is work to be done to do software proofs and security proofs, which is different from doing math proofs. Okay, we can be inspired by MathLib, but this is, I feel personally, quite different. The other one, of course, is AI assist. Everybody talking about this. If AI can assist us doing a lot of the proofs, which we found tedious, boring, also quite detailed, then maybe we can just do many more ambitious things that we never thought we could do. And that's kind of exciting for me. Of course, there's a ton of crypto algorithms, protocols, optimized implementation that we never verified, that we should verify. That's a no-brainer. But also things like building new verified compilers, new models for machines that expose side channels, doing side channel analysis tools. This becomes also much more possible, and I'm excited to see what comes through. And finally, the goal here is that the cryptographers already know what they expect from a system. But they write it in their own fashion, in a way which is very far and very divorced from deployed implementations. What I can hope here is that the papers about Signal can finally match the actual code that is running in Signal, and that's going to be the Signal Shot challenge. All right, so I'm going to stop there and ask for questions.
So thank you, Karthik. Are there questions? Yes.
Yes, you mentioned the users wanting to see the pre and post conditions. Can you speak a little bit about like what the difference was in experience between people who just wrote the project and you came in after the fact and tried to do the verification, and then the experience of people who actually got the pre and post conditions. In the latter group, did it actually change the way that they engaged in engineering at all, or was it just sort of like a nice to have for them?
The latter was the one who started from the beginning.
Right, where they
Yeah.
actually got to see the pre and post conditions. I'm sort of wondering if having those shape the types of engineering decisions that they made, or the way they shaped the code base or anything like that.
It did change, I
Perhaps can
think.
you sum up the question on just for the
Right.
audience?
So the question was, so you can imagine two styles of projects. One where people have already written the code and then we start doing the proof. So we add pre and post conditions. And the second one is where the programmers are already aware and they're perhaps even engaging in the writing of the pre and post conditions, and whether this changes the engineering effort in that particular project. I would say yes. I think often the structure of the code is different. Because you can imagine code factoring, right? You might imagine a piece of code that can really work in 5 different places and doing different things. If I is between 0 and 15, it's doing something. If between 16 and 32, it's doing something else. But the code is the same. So your mental model as a coder is to just kind of collapse that code, factor it out, put it in one function. But when you write pre and post conditions, you realize, oh, actually, this is being used for 3 very different purposes, and I want 3 different guarantees in those 3 different places. So in fact, it might be better to rename that function in 3 different ways so that it's clear what it's supposed to be used for and where. And so this might seem redundant, but actually in the logic of the project, this actually clarifies how this function is being used. And that's one example. So where it has an unexpected effect, let's say. But more generally, I think we found that the developers are writing a lot more debug assertions. When you start getting used to writing kind of pre and post conditions, it's a natural thing to say, hey, you know what, I should be checking that this value is between -2 to the 9 plus 2 to the 9 here. So let me just throw that debug assertion in there rather than just keeping it in the comment and not doing that. So yeah, it changes a lot the way people engage. Once you start writing logical formulas, you see logical formulas everywhere, I guess. So you start using them more.
Thank you. So we have one question online. I noticed that you chose hacks instead of NAS. And what is the main reason that you prefer hacks?
So hacks and NAS were kind of started more or less at the same time in the same group with 2 different philosophies. And NAS over time has become much more specialized towards lean because it's actually, obviously, lean is great. And whereas hacks was focusing more on F-star and ProVerif and these multi-prover style of verification. Nowadays, we are using lean a lot. And in fact, one of the big changes this year is that we are incorporating the NAS engine into hacks so that for the lean translation from hacks, you will basically be using NAS. That's basically what the plan is. So if you want to take Rust to lean, we believe NAS is the way to go.
Other questions? Yeah, please.
Yeah, I was curious about, so LibSignal has the CI ProVerif, but PyCalculus, so for example. But so the idea is that if they change the Rust code, they could get the text from Verif.
Ideally.
The link from Rust codes to PyCalculus.
Yeah. So we have a translation from the SPQR code through to ProVerif. This doesn't work very well. So any small change here probably breaks this. So I would like to say that, oh yeah, every time you change this, you can rerun the verification. What today they're doing is that they have their handwritten ProVerif, which is on CI. So anyway, but why does it need to be on CI? It never changes. It's that design. But it's on CI. It runs the handwritten ProVerif. They have the F-star, which is generated on every code change and it verifies. They have also the ProVerif that gets generated, but almost always needs some hand help before this can actually verify. But our goal is really, they should also be checking for security on every commit. That's not there yet.
Yes.
Does hacks handle unsafe code?
No.
Well, can you repeat the question? So that...
Oh, the question was, does hacks handle unsafe code? And the answer is no. But okay, let me put it this way. So we do use, okay, there is code which is unsafe for platform reasons, right? So if you use, if there's an intrinsic that you're using, which is only valid on ARM64 or whatever, it's unsafe because you cannot use it on other platforms. So what we do when you see an unsafe block, and I don't know what any of us does, we just kind of throw away the unsafe and just go in, and we try to treat it as it's just regular Rust code, okay? Until we hit something which we truly cannot handle, like star pointer, star mute, something. So and at some point, at some leaf, we will see an intrinsic, and we know that this is only valid on one platform, but we have specs for it anyway, so we will take it. So if the unsafe code is using kind of core libraries or some library which itself was unsafe, but we have a spec for it, we will see through the unsafe and still try to analyze it. But if it's using a particular memory transmute something which is deeply unsafe, then yeah, we won't deal with it.
Yes, Shao White.
Yeah, so correct me if I'm wrong. So in Project Everest, you were verifying cryptographic algorithms, but you start out with the algorithms and then you generated the verified code from there. Here with the protocols, it seems like you're starting first from the Rust or C implementations and then you're verifying it. Why not go back to the generation part? Because I mean, I can imagine some of the objections to this is it's very hard to write constant time algorithms this way, generating constant time algorithm and so on. But I imagine that if you do the generation correctly, it might be even easier generating constant time algorithms than actually having to think from first principle, like use human ingenuity to come up with one that's constant time and so on.
No, you're right. So if you're willing to use a domain-specific language, then you can do more, okay? So for example, the Jasmine language is, I would say, perhaps the best language for writing crypto algorithms today is Jasmine, because it looks like Rust. It's well type checked, but it's very low level, and it has a verified compiler down to multiple assembly platforms. It can check for side channels at various levels. So it satisfies that particular ink that you write in this domain-specific language, and you get out the thing with the highest level of guarantees without relying on any compiler. Okay, so that's one way of doing it, and that's what we were doing with Lodestar and in the Everest project. But that basically means that the crypto developer has to write in that language. Okay, it's possible that you might get convinced the crypto developer to write in Jasmine today if they are working in Bochum with Peter Schwaber or whatever, Manuel Barbosa. We could get our students, we could manipulate our students into writing F-star. And then I'm not sure they thank me for it. Some of them are in the room. But this is not, I can't ask the Signal people to write in F-star. It's not flying. I mean, it's not possible. Even the coders inside Crispin, I cannot get them to write in such a language. It's just the learning curve is too steep. And the skills are very non-transferable. Maybe Lean might break this, maybe writing in Lean and compiling might work because it's wide enough community that there is this transferable skill. But F-star definitely was not a language I would basically ask developers to write it. And so so this is more developer oriented. If you want the developers to write the code, Rust was a good source language. But then again, in an AI coding agent world, maybe we don't care about the surface syntax, and writing Jasmine may be as easy as writing anything else. So all these are questions which are open now, but yeah.
What's your hot take on that?
I think programming language syntax is a dead subject, except for deep bar conversations, maybe even in bar conversations.
Tomorrow.
Thank you. Other questions? Oliver.
Thanks for the great talk. It's good to hear about the details, the challenges. I was curious, do you have some thoughts as verification is more commonplace, more complete, is it going to allow software developers to change a bit the way they do it, be more experimental? Have you seen times like this?
We someone need to repeat the question because he was very far away.
So Oliver is asking whether as verification becomes more commonplace, has the way people develop software changed, maybe? Is that kind of roughly? Taking advantage of it? Yeah. So in our local case, we found that there were, so for example, we have this implementation of MLChem. We tried running it on IoT devices because somebody wanted it. and it was taking too much memory. And then we had to change the structure of a lot of that code in order to kind of reduce the memory usage and really change a lot of the way the butterfly and NNTT was done. A lot of the code changed. And our coders were not at all confident that they were doing the right thing. They could test, but still they were like very worried. In fact, because there are lots of little corner cases in things like NTT where you could easily be outside the range where the entity works. And you won't find it by testing. It only occurs once in 2 to the 64 tries that you will actually see that you actually went out of range. And so the verification allowed them to be confident that they could do these changes. Okay, that's one thing. In some other cases, I know in AWS, for example, they really now use Slothy, the super optimizer, to optimize their code, their assembly code even. And this is because, again, they have like ways of checking that the results are okay. So now you can do more kinds of optimizations that you would be afraid to do before, right? So I think that's the kind of thing that you're more likely to do. Also, if formal verification is so cheap, you might be more willing to verify assembly. This is what AWS does. They don't do it in a cheap way, but I can imagine somebody else who's doing it now will probably do it much cheaper than the Jasmine people or AWS did it. So you might be willing to do more things which were just so annoying before, or so unsure before, because you now have formal verification to back you up.
So I have one question about your final slide when you understandably commented that these proofs are different from math. So I put my math hat on. Do you use MATLAB in any way? Do you rely on MATLAB? Was it MATLAB useful in any way? Or no, I won't be offended, but but I'm just curious.
At the level at which we do the proofs, no.
No. Mm-hmm.
I mean, we use commutative rings for doing some field arithmetic stuff, but in a very trivial way. Nothing deep. My only
the grind version probably of commutative.
Right?
The grind version
the
of
grind
commutative
version,
rings.
The only interactions we have is when we have to tell it not to use MATLAB.
Stay away from MATLAB.
Omega will not solve this AI, all right?